Just give a couple of more minutes for see if some more people join. So there were 37 participants. Let's start. So I'm really excited to present you the Vitis network layer or VNX, which was the work that I did on the first 6 months when I joined Xilinx. And it has been some excitement over the XCC school where some both Professor Alonso and Michael Ablotz mentioned some networking side and some research in this area as well. So let me grab my laser pointer. So this has been mostly a research project. It's not really a product, but that doesn't mean that it's not really reliable and useful. So the goals of this project was to provide networking on Vitis platforms to support XCC and research initiatives. So as Professor Gustavo Alonso mentioned on Tuesday, there has been very little work, or it's not really that many projects that work out of the box with Alveo cards or FPA in general to provide networking support on the FPGA side. So this is just the very beginning. So there are much work to be done in this area, and we're happy to discuss further at the end of the session. So the idea was also to provide an easy integration with user kernels, where you can just grab this as a framework and just to plug your kernels, and that will be able to communicate directly with the network. The target for the initial target is people that are working with distributed computations, inference, training, database acceleration, HPC, and type of workloads, distributed workloads. And it's really not intended for networking acceleration or smart NIC type flows. Even though that can be used in that area, it's not really, it's not the main goal of this project. Just to give you a little bit of background, so there was a question to Professor Alonso about his thought on the Xilinx TCP/IP, and I'll just let me give you a quick review on the history of the TCP/IP stack for Xilinx devices. This started on maybe late 2013 or 2014 on the Xilinx research labs with Michaela team and other members working for that application that she mentioned on the Memcache. So she worked with some of the ETH PhD student at that time, David Saber. And after the project was done, so ETH took more or less ownership of the TCP/IP, and they continue developing actively on that area and that code. So in late 2017, as part of my research, I started collaborating with ETH, and I did a branch or a version of this, and I ported it to HandyG. And this leads to the project to a Limago, which is just a little bit try to be a framework using the TCP/IP to provide networking on Alveo on general FPGA general. So at some point, ETH also upgrade their code and support 100 gigabit. And at this point, this is just for Vivado flow. So this is not actually for Vitis flow support. So the integration with your kernels and the networking is a little bit, is very challenging, complicated, and using the Vivado flow. So the challenge of this project is to provide or to integrate this functionality on the Vitis flow directly. So I started working on this on early March, this past year, sorry. And in October 2020, we released VNX. And a month later, ETH released their branch, let's say, with Vitis support. So I will say these two branches are siblings. They have some difference, but they come from the same piece of code. What was the one originally designed at Xilinx Research Labs at the very beginning. You might have come across some other solutions or research solutions or papers that mention about TCP/IP implementations. It's more likely that many of them or most of them use this original implementation. So I also put in this slide some of the people that have worked on this project. So, and we will have the opportunity to hear from Chenghao He later after this presentation. So, and just again, as a background to show you the current ETH infrastructure in terms of networking. So just a reminder, one of the Alveo interfaces is connected directly to the switch, and the other one is connected directly to another FPGA using the interface one in a point-to-point fashion. So let me move to the VNX architecture itself without going into that many details about the HLS implementation of the core. So if in our Vitis platform, we have the static regions, which also is called platform or shell, depending on who is talking, and the dynamic region, which is the user region. So the Alveo cards, as I mentioned, provide the Ethernet, 100G Ethernet interface, and some of the Xilinx platform expose those gigabit transceiver pins directly to the user logic, as well as the reference clock for those gigabit transceivers. So the basic architecture of this project includes a CMAC, which is a 100 gigabit medium access controller IP that translates from the physical signals on the gigabit transceiver pins to a 512-bit access stream interface. And this is the CMAC kernel is a current interface specific configuration. On top of that, we have the network layer, which includes some of the very basic network functionality. In this case, for VNX, it's only UDP. A little bit on this a little bit in the next slide. So, and this network layer is really can be used across multiple different platforms without doing any kind of change. And on top of that, at this point is when you can connect your user kernel directly to the network layer, and using a simple access stream interface with a sideband channel to identify one of the connections, you just basically can communicate with the network directly without doing anything else. So this project is built on layers, which makes it very easily to adapt to a different architecture, or to replace the user kernel and implement something a little more complicated, or to match your architecture. And the VNX supports multiple interfaces and cards, and currently U250 and U250, U250 and U280 are supported. For U250 and U280, we can support both interfaces with VNX, just running a simple makefile command. In terms of the network layer, so as I showed in one of the first slides, this is based on Limago. And the network layer itself provides an ARP module, which also basically is translating MAC addresses and IP addresses. And the ARP table can be accessed from the host. And the ACMP module provides basic ping functionality. And on top of that, the UDP module that provides the transport protocol. And the model itself contains a 16 entries table that can also be accessed from the host and has to be populated before actually doing any communications. As I mentioned, so the interfaces are 512-bit access stream interfaces with in the user side, you have the TDES, which is just basically matching or querying this table to identify the different connections. So in terms of the application of some of the examples that are provided in VNX, so the very basic examples, this is the very basic, this part we have described this, and just have two kernels, one that reads from memory and generates some memory in a stream and feeds it directly to the network layer. And the other kernel provides a stream or reads a stream data from the network and put it on the memory. This can be thought as a very basic inter-network card where you can actually move data from your host to the network. But in this case, there is a limitation or a catch that the data has to be multiple of 64 bytes. And a little bit more complicated or more interesting design is the benchmark kernel or I design, which basically we are providing a benchmark kernel that allows us to measure or to benchmark throughput and latency in our application. So the benchmark kernel is comprised of two more low-level implementations, which one is the traffic generator, which will generate some patterns to measure either throughput or latency, and the collector, which is gathering the information of the experiment. So when I mentioned in the first slide that this is meant to be for distributed computation, so if we go back to the very basic 5-step code execution on a heterogeneous system, so one of the challenges here is that you might not have all of the FPGA in the same physical server. And even though on ATH, the FPGA or the Alveo cards are isolated on VM. So how do you actually can perform or run these 7 steps in a distributed fashion? So one way will be to log into the different systems and run each of these steps manually, but that will be very challenging, error prone, and the synchronization will be a nightmare. So for that reason, we also use Dask, which is a Python packages that provides a flexible library for parallel computing on Python. And we wrote with, together with Peter Oden, we wrote a Dask class that builds on top of Pink that allows us to execute those 7 steps in a distributed fashion from a single source code. So we use Pink on Alveo as a host code, and our host code is provided on Jupyter Notebook, Jupyter Labs Notebook, and the Dask class provides distributed communication, remote buffer allocation, and also remote task execution. All the same functionality as Pink, but distributed, which is really, really nice. Just so it's worth mentioning that in order to perform this kind of this task doesn't use the Alveo card network, it uses the regular network. So going back here, if you think about this example where you have to configure both leaders and followers, so when you actually move in buffers and scheduling executions, you are actually using this network. So in order to use this network, you have to do it manually and configure your kernels directly. So that leads me to some of the results, a demo, and conclusion of this presentation. So I used the benchmark application to benchmark this implementation, the VNX implementation, in 2 scenarios. One is point-to-point communication, and the other one is using the 100 gigabit switch. So if you recall, we can do that directly on the ETH infrastructure, and because VNX support both interfaces, we can actually generate a single XLB file that allows us to measure or to run the experiments with a single XLB file. So in terms of throughput at application level, on point-to-point, the performance is really good. And it's a little bit after, let's say, 256 bytes payload size, the throughput is much better than the theoretical UDP throughput, because we're actually using, we're not limited by the switch itself, which is capping the throughput at 100 gigabit Ethernet. And with the switch, we get after 256 bytes, we get the theoretical throughput. And in terms of latency, or I will say round trip time, the application, so in point-to-point, we get around a microsecond, which point-to-point, as direct communication should be 500 microseconds, and you will see the standard deviation is negligible for this application. I mean, when you put the switch in the middle, the latency or the round trip time increases as expected because of the switching time and things like that. And in terms of resource consumption, so in this chart shows you the resource consumption for Alveo U50, Alveo U250, and Alveo U280 for three of the main resources on the FPGA. And as you can see, the CMAC and the network layer in the worst case scenario only uses up to 7% on VRAM. And in terms of the full design, including the platform and the applications, in the worst case scenario, again, which is a U50, is a maximum of 25%. So this gives you a plenty of space for your application and to experiment and do distributed computation. So with that, I would really like to show you a demo on a film-based Resonant 50 on two Alveo U280 that we work together with the research labs here in Ireland. And this integrates both a Resonant 50 building with film-based and using the automatic partitioner that Michaela mentioned yesterday. So without even further let me show you the demo. This demo, I'm going to demonstrate distributed inference using a film-based Resonant 50 neural network split into two Alveo's U280 cards. The intermediate results of device 0 is sent to device 1 using VNX. I will also be using ping to drive the host code of this demo. On top of that, I will be using Dask that will allow us to program, configure, send, and receive buffers from the different Alveo cards in this demonstration. In the figure, you can see the different components of this demo. On the left-hand side, we have device 0, which gets images from the host, does some processing, and sends the intermediate results to the device 1 using VNX. This device 1 finalizes the computations and produces the labels and all the results of the inference that can be later retrieved. So let's begin. Let's start by loading some of the necessary Python packages to run this demo. After that, we are going to connect to the task cluster that I assume that is already configured for this demonstration. As you can see, there are two workers and each of them corresponds to one of the Alveo cards. Now we're going to run a very simple function on each of the different workers to retrieve the name of the worker as well as the Alveo shell configured on each of them. As you can see, we are using Alveo 3B and Alveo 3C, and each of them has a Xilinx U280 XDMA shell. We are also going to load some Python code that does some of the magic to proxy Python over Dask. After that, we can program each of the different Alveo cards, which is corresponding XCL bin file. So this takes a few seconds to load. And as you notice in the remote worker, the XCL bin file is sent through the network and programmed on the device. Once this is done, we can have a look at the different IPs on the different workers. So in the worker 0, there are some CMAC, DMAs, and network layer. On the device 1, we also have two DMAs, CMAC, and network layers. Now we can verify the network link on our demo. So as you can see, both devices have network link, so we are ready to go with our demonstration. But first of all, we need to configure the network kernels of the two devices with the IP address and the UDP table, connection table. So once this is done, we can start doing actually some work with the hardware, and we're going to load the weights of the fully connected layers on the device 1. So now we're going to define an inference function, which is going to run the inference individually for each of image. So one of these, the function is defined. We can actually run the inference. We can load a few images, and we can run the inference after that. So once it's done, we can actually show the results. So as you can see, I've run 12 images here, and each of them I'm showing the images as well as the result of each of the devices. So if we have a look at the function that is actually doing the inference, you will notice that we are defining some buffers in the local worker and in the remote worker. We pre-process the image and start the worker, the remote worker, and transfer the image to the local accelerator, which will transfer the intermediate result to device one. And after that, we retrieve the result from the device and return that result. So just very quickly, let me unpack the demo. So what I've shown you here is a demonstration on ETH infrastructure that uses both Jupyter Lab, Ping for Alveo, Ping for Alveo, and the Dask framework. So we are using Dask and Ping to program both FPGAs, both the leader and the follower, what you want to call it. We also program the network interfaces for both devices and configure the UDP table. And after that, we can actually start running the inference. But first, we have to configure or to load the fully connected weights on the device one for the fully connected layers. And at that point, we can start running our demo, right? We move images, image by image here, just for this demo, image by image to the device 0, which does some processing and move the intermediate results to the device 1. And that's result that this produces the labels of the result, and we can retrieve that with Dask as well. So as you can see, this is if you don't do it or you have a way to do it distributed, the configuration to run this is a nightmare. So just in conclusion, so this presentation, I show you a handy UDP IP networking solution on Alveo cards using Vitis that we are providing 2 examples with companion notebooks. The interface between the network layer and the kernel is very simple, and it's very easy to integrate your kernel or compute kernels directly with the network. So because this is UDP, it's very lightweight, but it's unreliable, right? So, and it's ideal for point-to-point or control environments where the packet loss is very small, sorry. We also have provided a Dask class for the distributed configuration. And just to be clear, this is not a specific of VNX. Finally, this is an open source repository or project that you can get there, grab it, and try it out. So what is also really interesting, because we are using Jupyter Notebook, the notebooks or the companion notebooks that we are providing for the examples already contains the result of the experiment I just ran for both the basic and the benchmark application. So I really encourage you to go there to the repository and have a look at the notebooks.